In this video, we introduce the hypothesis test for one population mean when the standard deviation sigma is known. If the population standard deviation sigma is known, a hypothesis test performed for one population mean is called one mean z-test or simple z-test. A z-test is a hypothesis test for testing a population mean mu against a supposed population mean. The z-test assumes nobody distributed variables or a large sample size. Then the central limit theorem guarantees a nobody distributed sampling distribution. In addition, sigma, the standard deviation of the population, must be known. In real life, this assumption is seldom fulfilled, and thus, the z-test is rarely applied. However, it is the simplest hypothesis test, and thus, a good subject to start with. We use the 6-step procedure to do this two-tailed hypothesis test. To give you more background information of this small case, please let me read this case to you at first. Jamestown Steel Company manufactures and assembles desks and other office equipment at several plants in New York State. At the Fredonia plant, the weekly production of the model A325 desk follows a normal distribution with a mean of 200 and a standard deviation of 16 desks. Now they introduce a new production methods, and the vice president of manufacturing would like to investigate whether there has been a change in weekly production for the model A325. The mean number of the desks produced last year, 50 weeks, because the plant was shut down 2 weeks for vacation, is 203.5. The question of hypothesis test is the mean number of desks produced differently from 200 at the 0.01 significance level? The null hypothesis H sub 0 is mu equal to 200 desks, and alternate hypothesis H sub 1 mu unequal 200 desks. This is a two-tailed test because the alternative hypothesis does not state a direction. The level of significance 0.01 is given when testing a hypothesis about a population mean. If the population follows the normal distribution and the population standard deviation is known, the test statistic is z and is determined as previously discussed. In this example, we'll use z equal to x bar minus mu over sigma divided by square root of n. Since this is a two-tailed test, the level of significance 0.01 is divided in 2. So 0.01 divided by 2 equal to 0.005. And 0.005 is placed in each tail and becomes the region of rejection. To find the critical value using the z-table, you may use either two-tail or one-tail z-table. In this given one-tail z-table, we look for a probability equal to 1 minus alpha over 2 equal to 0.995. And it's about here. Actually, it's in the between of these two values. We can then identify the z value in this cell is 2.576. So the critical value are plus minus 2.576. Based on the given sample, with a sample mean of 203.5, provided that mu equal to 200, sigma equal to 16, and sample size n equal to 50, we can then compute the test statistic as follows. Z equal to x bar minus mu over sigma divided by square root of n equal to 203.5 minus 200 over 16 divided by square root of 50, which is given by 1.547. Because 1.547 does not fall in the rejection region, we decide not to reject the null hypothesis H0. In conclusion, the sample information fails to indicate that the new production methods resulted in a change in the 200 desks per week production rate. However, we did not prove the assemblage rate is still 200 per week. We fail to disprove it, which is not the same as proving it to be true. To showcase the one-tail test, we study this new development of the case. Suppose instead of wanting to know if there has been a change in the mean number of desk assemblers, the vice president wanted to know if there had been an increase in the number of unit assemblers. Can we conclude, because of the improved production method, that the mean number of desks assembled in the last 50 weeks was more than 200? We still have a level of significance alpha equal to 0.01. Based on the problem, we can then form the null hypothesis in the first steps as follows. In this one-tail test, we have H sub 0 mu less than or equal 200 desks. H sub 1 mu large 200 desks. As we know, the level of significance is 0.01. In forming the decision rule, the critical values for a one-tail test are different from a two-tail test at the same significance level. In the two-tail test, we split the significance level in half and put half in the lower tail and half in the upper tail. In a one-tail test, we put all the rejection region in one tail. Using J table, check the probability value of 1 minus alpha equal to 0.99. We find the closest value. Then we find that the Z value is 2.326. Because we have the same sample as that in the two-tail test, we actually obtain the same test statistic. That is, Z equal to x bar minus mu over sigma divided by square root of n equal to 203.5 minus 200 over 16 divided by square root of 50 equal 1.547. Again, the test statistic is not in the region of rejection. In conclusion, the sample information fails to indicate that the new production method resulted in an increase in the 200 desks per week production rate. However, we did not prove the new assembly rate is significantly less than 200 per week either. We fail to disprove it. We have previously shown a case of upper tail one-tail test. In a lower tail one-tail test, the procedure is the same, except that the critical value is a negative Z value. We may use the Z table to find the Z value, given the probability equal to the level of significance. The rest of the testing is the same. We now provide a different perspective on the test statistic in terms of p-value. A p-value is the probability of obtaining test results at least as extreme as the results actually observed, under the assumption that the null hypothesis is correct. The lower the p-value, the greater the statistical significance of the observed difference. A very small p-value means that such an extreme observed outcome will be very unlikely under the null hypothesis. In the previous one-tail upper tail example, we already know the z-score was 1.547. We may round the computed z-value to 2 decimal places, 1.55. Using the given z-table, find the probability of a z-value of 1.55, which is 0.9394. Then the p-value is given by 1 minus 0.9394, which is equal to 0.0606. So the probability of finding a sample mean greater than 203.5 when the population mean is 200 is 0.0606. Thus, the p-value of 0.0606 is greater than the significance level of 0.01. So, the null hypothesis H sub 0 is not rejected. For the case of two tails, the two-tail p-value is 2 times 0.0606 equal to 0.1212, as we show here. Thus, the p-value of 0.1212 is greater than the significance level of 0.01. So, H sub 0 is not rejected either. Based on the above reasoning, we can also use p-value to conduct the hypothesis testing. If the p-value is smaller than the significance level, we reject the null hypothesis H sub 0. Otherwise, if the p-value is larger than alpha, H sub 0 is not rejected. In fact, a p-value can not only result in a decision about the null hypothesis, but also demonstrate the strength of the decision itself. Usually, a very small p-value, such as 0.01, indicates that there's little likelihood that the null hypothesis is true. If p-value less than 0.05, we have strong evidence that the null hypothesis is not true, and so on. On the other hand, a p-value of 0.2033 means that the null hypothesis is not rejected, and there's little likelihood that it is false. In summary, in this video, we have discussed the hypothesis test for the mean with long standard deviation. In specific, we have talked about two-tail test, one-tail test. We have also introduced the concepts of p-value and shown how to use p-value hypothesis testing.